Today we're solving Leetcode 3650 minimum cost path with edge reversals. This problem is a great interview test of whether you can model constraints correctly and then apply Dijkstra's algorithm on a cleverly transformed graph. If you understand this solution, you'll be very comfortable with advanced shortest path variations. You're given a directed weighted graph with n nodes. Each edge has a cost. Each node has a switch that can be used at most once. When you arrive at a node, you may reverse one incoming edge and immediately traverse it. Reversing an edge costs double the original weight. The reversal only applies to that single move. Your goal: find the minimum cost to go from node 0 to node n1. If it's impossible, return -1. Walk through example 1. There are 4 nodes, numbered from 0 to 3. The directed connections between them are as follows. There is a path from node 0 to node 1 with a cost of 3, a path from node 3 to node 1 with a cost of 1, a path from node 2 to node 3 with a cost of 4, and a path from node 0 to node 2 with a cost of 2. The optimal route starts at node 0 and goes directly to node 1, which costs 3. Once at node 1, the edge that originally goes from node 3 to node 1 is reversed so it can be used in the opposite direction. Reversing this edge doubles its cost, so traveling from node 1 to node 3 now costs 2. Adding these together, the total cost of the path is 5. This problem looks complicated because of the switch only once rule. But here's the key modeling insight. You can treat every reversed edge as a new directed edge with cost 2 times W. Once modeled correctly, this becomes a standard shortest path problem. No DFS, no DP, just Dijkstra. A brute force approach would track which switches were used, track path states explicitly, explode into exponential complexity, completely infeasible for n up to 50,000. For each original directed connection from one node to another with a given cost, we create 2 possible paths in a new graph. First, we keep the original direction and cost exactly the same. This represents using the edge as it was originally defined. Second, we also add a path in the opposite direction. This reversed path has a cost that is twice the original cost, representing the extra expense required to reverse the edge. After doing this for every original connection, the problem becomes simpler. We now only need to find the cheapest route from node 0 to node n-1 in this newly constructed graph. This works because you can only use the reversed edge when you arrive at that node. Each reversal is already paid for by the doubled cost. Since all edge weights are positive, we want the shortest path. We use Dijkstra's algorithm with a min heap. The solution defines a method that calculates the minimum cost to travel from node 0 to node n-1. First, it builds a graph representation. For each edge given in the input, 2 connections are added. One connection keeps the original direction and cost. The second connection goes in the opposite direction and has twice the original cost, representing the cost of reversing an edge. Next, the algorithm uses Dijkstra's shortest path method to find the cheapest route. Keeps a list of the minimum known cost to reach each node and initializes all of them to infinity, except for node 0, which starts at cost 0. A priority queue is used to always explore the node with the lowest current cost. While the queue is not empty, the algorithm removes the node with the smallest cost. If this cost is already higher than a previously known cost, it skips that node. If the current node is the destination node, the algorithm immediately returns the total cost, since Dijkstra guarantees this is the cheapest possible path. Otherwise, the algorithm checks all neighboring nodes reachable from the current node. For each neighbor, it calculates the new total cost. If this cost is lower than the previously recorded cost for that neighbor, it updates the cost and adds the neighbor to the priority queue. If the destination node is never reached, the function returns -1 to indicate that no valid path exists. The time complexity of the solution is proportional to the number of edges multiplied by the logarithm of the number of vertices. This comes from using Dijkstra's algorithm with a priority queue. The space complexity is proportional to the number of vertices plus the number of edges. This space is used to store the graph structure and the array that tracks the minimum distance to each node. Overall, the solution runs efficiently and fits well within the given constraints. Common mistakes and edge cases. Overcomplicating with DP or state tracking. Forgetting reversed edges cost double. Using BFS instead of Dijkstra. Not handling unreachable destination. Recap. Model edge reversals as new directed edges. Assign correct costs. Run Dijkstra normally. Interview tip. When a problem adds special moves, ask if they can be modeled as extra edges.